My project involves using photocatalysis to remove common contaminants found in aquaculture and looking at coupling this with photovoltaic cells so as we can power it using solar power. Our freshwater is a very limited source at the minute. There's less than 1% of the world's freshwater is actually available to us. So this is the only water that we can drink. So we need to make sure that this water is pure enough to actually use and it's safe for humans. Photocatalysis is when you use a light to excite a catalyst, which can be something as simple as titanium dioxide, and that's something that we use every day. It's in everything white that we use, so like toothpaste, in the road markings, like the white road markings, and on the top of sweets like Skittles and M&Ms, it's used for the writing on the top of those. So I use that, and when you shine a bright light on it, it creates a lot of reactive oxygen species, and so they attack the target contaminant in the water and break it down into less harmful components. So this is kind of a typical experimental setup for me. So in a beaker I have water with trace amounts of each of the contaminants that I'm looking at. So to that beaker I'm going to be adding some of the catalyst. So this is the titanium dioxide, the catalyst that I use. And it's got a magnetic stirrer in it as well, so as we can kind of let it stir the whole time. So the LEDs that I'm using at the minute are single LEDs, but you can get a whole different type of range of LEDs. So these are other ones I've used in the past. It's a ring of strip LEDs, so we kind of just use whatever one suits best to the purpose that we're using. These light up in a circle normally around the beaker, but these just irradiate it from the top. As the light shines onto the catalyst, it'll start to produce a lot of reactive oxygen species, which will then break down the target contaminants that are in the water. It's really important because by the year 2050, there's going to be an extra third on the demand that we currently have for this water. So we really need to make sure if we're polluting it that we're removing the contaminants and making sure that it's safe. As well as this, we've been developing detection and analytical methods for monitoring the concentration of these compounds continually. So we've developed an online detection method that is able to monitor the concentration of emamectin benzoate and MCPA in the water as we treat it, and this has the potential to be used on a much larger scale as well. Because drinking water is such an important commodity at the minute, we need to make sure that it is pure enough for humans to drink and that it's not damaging the environment as well. My project involves looking at two main contaminants and kind of looking at how we can remove those from the water. So the first contaminant that I've been looking at is a thing called MCPA. It's the most commonly observed pesticide around the world, and it's a massive problem in Ireland because we have such high amounts of agriculture here, and because of our weather as well, because it rains so much, a lot of it runs off into the streams and the bodies of water, so it causes a lot of water pollution. The next step in this would be to analyse what is actually in the water that we have been shining the UV light on. So we're going to take a sample from it and put it into this 6-port valve here. So some of the sample is going to be stored in this 20 microlitre loop, and then when we open the valve it'll be pushed through with the electrolyte that we have running through the system, and it'll go onto the surface of the screen printed electrode that we have here. So we're going to attach that electrode to the computer through a potentiostat, and then whenever the sample runs over the electrode we're going to get a peak on the graph here, and that represents the concentration of the contaminant in the water. MCPA was found in over 2/3 of the bodies of water examined by the Environmental Protection Agency in Ireland. It's really toxic. So it's toxic to the fish that come across it. It's also toxic to humans. So obviously this is something that we don't want in our drinking water. When MCPA breaks down, it forms a product called CMP, and CMP itself is actually more toxic than the MCPA. So it's also been found in water samples across Ireland. So whenever we're removing the MCPA, we want to look at something that could also remove any CMP that's formed. And then the second contaminant that I'm looking at is called emamectin benzoate. It's a type of antibiotic that's used in a treatment called SLICE, which is used to treat sea lice on farmed fish. It's the main component of this treatment, and it's really toxic to everything that comes across it. So it doesn't dissolve well in water, so it always ends up in the seabed. Normally it's not too much of an issue because initially it was just found underneath the fish farms. However, it's spreading a lot further now. It's been found a lot further afield, and obviously this is contaminating our water. It's something that we want to get rid of. So because these contaminants are issues all around the world, this is going to be of interest to researchers everywhere and everyone looking at how we can purify our water and how we can enhance the current water treatments that we have, because a lot of them don't work too well at the minute and they need to be improved. While this work shows that these two contaminants can be degraded effectively, it can also be used to show these compounds as model targets, so it can show that this system can be used to treat a lot of other organic contaminants within our water and to degrade them to purify the water. The next steps within this research would be to look at how this would work on a larger scale, so to couple more with industry and see how this could be used in real life. It would be great to also look at how our detection method could cope with larger volumes of water passing through and how it could give an accurate representation of what's actually going on with raw water and how it would work in real life. I have really enjoyed working on this project because of the real life applications and how you can actually see how it would make a difference and how it could be used commercially. So I would really like to move into industry and look at that sort of side of it and kind of look at how I could develop research from the lab stage into actual something that could be used in real life. My project is funded by the Bryden Centre and they are very supportive of all our research. There's a lot of collaboration within the Bryden Centre, so I work closely with colleagues in Letterkenny and in Scotland who all work on the same sort of projects as me. The Bryden Centre is very focused on having industrial partners and doing research that can actually be useful in real life. So it's great having the support of industry to guide you in the right direction and show you how things can work on a larger scale and how things work commercially.